Well, hello everyone, and welcome to Virtual Precision Livestock Farming Day. I'm Dave Thompson from Michigan State University, and I'll be moderating today's webinar. Our program today is designed to give you an early look at some emerging technologies in precision livestock farming. Examples from cattle, swine, and poultry production will be described by researchers who are leaders in this field. Each researcher was asked to say a few words about how the technology works, then describe how it can benefit both farm economics and animal well-being. They'll also say a few words about key challenges facing introduction of these technologies into the real world. And I'll say a little bit more about each speaker when we come to them. Before we get started, though, I want to say a few words about Zoom logistics. If you have a question, you want the panel to consider, or you're having trouble with the webinar, please use the QA function. If you're connected by phone, you won't be able to chat or ask questions, but you can text questions to Megan at this number. There will be polls right after the third and fifth talks. Just click the appropriate button on the screen, and the panel will respond to some of your questions right after each poll. And please use the raise hand button if you need someone to help you make the Zoom webinar work. Now we're going to lead off with Drs. Janice Siegfried and Madonna Benjamin at Michigan State University, who will provide an overview on the precision technologies field. Janice and Madonna.
Hello, everyone, and welcome to our Precision Livestock Farming Field Day. I'm Janice Siegfried from the Department of Animal Science, and I've been using technology to monitor animals for over 15 years, starting with pedometers in beef cattle, and then accelerometers on chickens, rumination monitors on dairy cows, and now computer vision with swine.
And my name is Madonna Benjamin from the College of Veterinary Medicine. I have been fascinated and involved with technology to design ways to assist producers and stock people and to address where livestock can economically bridge with.
So we'll be kicking things off with a quick introduction to the topic of precision livestock farming, PLF for short, and the production challenges it may help us address. Then we'll turn you over to some researchers who are working actively to develop PLF. They'll talk to you about some of the specific technologies they're using with animals in agriculture, ranging from dairy cattle to poultry. Throughout the field day, we encourage you to ask questions by texting in the chat box, and we will have opportunities for you to be seen and heard during interactive discussions with the speakers. So let's get started. Madonna, what comes to mind when you hear the term smart or precision farming?
Precision farming. Well, I think first of using technology to monitor and manage crops, whether it's at the level of the field or plot or even down to the rows. And then another common area are the systems that monitor temperature and humidity in the barns.
Yeah, barn management systems are probably what initially pop into most of our minds when we're thinking about using technology in animal agriculture. But when we're talking about precision livestock farming, this term implies something different and a bit deeper. So for our discussion, PLF is technology that measures at the level of the animal to provide you with information that lets you monitor and manage your herds or flocks down to the individual cow or pig or bird. So we aren't talking about technologies and management systems that operate at the level of the barn that many of you may already be using, such as monitors for temperature or airflow, water use, or feed levels. But familiarity with those types of tech will make it easier to take the next steps to using technology that monitors the animals themselves.
Oh, absolutely. And in fact, many of these existing barn management systems, such as Big Dutchman, Hogslat, Maximus, will likely provide the platform or infrastructure for the implementation of PLF. Oh, Janice, how did you become interested in PLF?
Well, as an ethologist, I'm always searching for ways to capture information about animal behavior to answer my own research questions. And working with animals in commercial agriculture, I'm constantly confronted with trying to gather more information from animals that all look alike, are housed in large groups, and live in environments where it can be hard for me to watch or track an individual over time. It also takes a lot of time and effort to observe large numbers of animals over the course of an experiment or over the course of a production cycle. And the other problem I had was that my presence in the barn often changed the animal's behavior. So what I was recording and collecting data on might not have been what they were normally doing if I wasn't around. So I started turning to technology to remotely monitor animals in ways that wouldn't change their behavior. So I could see what they were really up to and how they were responding to different environments or management or other animals in their group or to issues like heat stress and disease. What about you, Madonna? What drew you to precision livestock farming?
As a practicing veterinarian, I was frustrated with the increasing rate of livestock mortality and lameness within the industry, not just on our farms. And when you look back, we measure success based on key production indicators such as growth or net number of animals raised. And yet our health assessments such as lameness and changes in body condition are highly subjective. In 2015, I read a publication on computers to detect ripeness of mangoes. This was based on the depression of the fruit flesh caused by the overripeness. So in other words, the computer detected overripe mangoes among thousands moving through a conveyor belt. And that was it for me. I believe if a computer could quantify the shape of a mango, we could quantify the body condition and lameness pattern of a pig.
That's great. I love that it all started with a mango for you.
Now we're using infrared cameras and related software to predict lameness patterns of sows, and we're using 3D imaging to quantify changes in body condition. Our goal is to give farmers a decision tool to compare these new quantitative assessments to their key production indicators.
Okay, so between the two of us, we've used many of the various types of PLF technology that are being used to capture data from animals on farm. In the next few slides, I'll provide some examples of the main categories of each of the types of tech being used in PLF, leaving our speakers later to fill in some of the details. So first, there are a number of different kinds of body-worn sensors. These range from simple passive RFID tags that you may be familiar with that can be used to record animal visits to resources like feeders or link animal identities to weights on scale. There are also ultra-wideband tracking systems that actively transmit information about animal location and movement. Many kinds of body-worn sensors also use accelerometers to provide information about the amounts and kinds of animal activities that they're doing. Some of these are already commercially available for use with cattle and swine in particular, but there are body-worn sensor systems that are being developed for use with poultry research too. A second category of PLF that's worth mentioning contains the technologies that monitor sound. These can either be remote, using microphones positioned in barns, or they can be body-worn, using microphones on the animals themselves. Most of the remote systems detect sound at the level of the entire group or pen, while the body-worn sensors more typically link sounds down to the individual animal that made them. Either way, they capture acoustic information from animals that can provide insights into their health or feeding activity, or even their distribution in the barn. Cough and rumination monitors are currently commercially available for pigs and cattle, and other monitors are being developed that analyze vocalizations or the sounds of animals' jaws moving. Another broad category of PLF uses remote-based technologies, a large group of which are vision-based. Computer vision encompasses a range of image-based technologies and their underlying processing systems. And these capture and analyze either video or still images of a variety of different types. In addition to capturing standard visible light photos or videos, like the ones we capture with our phones or traditional cameras, there are cameras that can capture images using infrared wavelengths. These can work to capture images under low light conditions or can render a thermographic image that shows the body temperature of the animal. Other camera technologies can capture three-dimensional images to create information about body shapes and depth that can be useful in estimating weight, body condition scores, or even individual animal identities. Most cameras are mounted in stationary positions in barns, often from the ceiling. Others might be mounted at animal level to use snout or nose patterns for facial recognition, or to capture the temperatures of eyes or ears for more accurate thermographic information. However, some cameras may move along tracks, such as down the row of cages or aviaries in a commercial poultry barn. There are even some drones being tested for use in barns.
Really? Drones?
Yep. They're being developed for use in open barn poultry facilities, like the ones we commonly use to raise turkeys or broiler chickens. Though, as you can imagine, you have to be careful not to frighten the birds, and they do kick up some dust.
Okay, so we have a lot of cool technology, but what are the practical challenges that can help us address in livestock and poultry production?
Well, I think one of the biggest advantages PLF gives us is that ability to look at and manage animals as individuals. So this can help us address labor and record-keeping challenges, ranging from simply counting animals to tracking and treating problems at the individual animal level, like lameness, or to more precisely carry out routine management tasks, like breeding, or to feed more efficiently to meet a particular animal's needs.
So essentially, PLF lets you go beyond the barn averages and to drill down further.
Right. So this is really similar to using smart ag with crops, where you can zoom between information at the level of the whole farm down to the level of that single seed drilled in a particular row on that field. So the seed is planted in a specific set of soil, has a specific set of moisture and solar conditions, and therefore that seed needs a particular amount of water or fertilizer or pesticide to grow to its best ability. PLF can bring the focus down to the level of each specific cow in the barn, pig in the pen, or chicken in the aviary. And then you can bring data from all those animals, plus other information on the farm together to get that big picture.
Think about it. Having precise data from individual animals also improves traceability and transparency for quality assurance programs. It can improve consumer trust and metrics to return on investments on treatments. And going back to my original interest in using technology, PLF can help us replace those subjective assessments to important conditions like lameness or body condition, and standardize those measures over time and across people or facilities.
Exactly. So another benefit to PLF is that we can use it as a tool as humans to work smarter. The best PLF really should let producers put our limited human labor to better use. So PLF can be used to do some of that repetitive, tedious work. For example, performing activities that are time-consuming, such as watching cattle for signs of estrus, or counting weaned piglets as they move to maintain inventories. PLF will let people redirect their efforts to tasks that require our smarts and human ingenuity to solve problems. So generating lots of data is a strength of PLF, but this can also pose a challenge. If data are continuously being generated in real time from every animal on a farm across that animal's entire time on the farm, the data quickly mushroom into a nearly unmanageable, almost incomprehensibly large cloud of data.
Right. An area of real need is a good user interface and data management system that pulls it all together and lets a producer make a decision and then take action.
Yeah, the information from PLF isn't useful if it doesn't come together in a useful way.
Exactly.
So though PLF holds a lot of promise, that doesn't mean it comes without challenges, right? Here are a few that we think are the big ones for all types of PLF in general. One of the first is keeping the systems affordable as they become commercialized. From our experience, many of the individual components that we use to build a PLF are relatively inexpensive. So you could build a do-it-yourself computer vision system with 2 cameras and a computer for less than $1,000. The challenge and the cost come when you bring in someone who has computer science skills that are needed to turn those images into valuable predictions, and then to commercialize the system in a way that keeps it affordable, but of course, also turns a profit for the company that made it. Another challenge is the cost of the system relative to the value of the individual animal. If you have a dairy cow and she has considerable commercial value as an individual, as well as potential in terms of her milk yield, and she's likely to be in your herd for a while, investing in a $35 body-worn sensor for her that leads to either better breeding success or milk yield, that'll be worth it. But a $35 tag for a broiler chicken, that just isn't going to fly. This also leads to the issue that some of the returns that PLF bring may not lead to direct returns in terms of dollars. What I mean by this is that if you're able to continuously monitor your individual animals, you may be able to better ensure their welfare or reduce treatment costs or meet customers' needs for assurance. But you'll have to keep in mind that that return on investment is balanced by the cost of purchasing and using the tech. We also need systems that are tailored to fit the particular species and your particular farm. Systems developed under one set of conditions or for one certain type or breed of animal will need to be adjusted before they can work under another set of conditions. Mm-hmm. So if, for example, we were to use PLF that was trained to predict lameness in pigs, but it was trained using finishing pigs, it might not be able to detect lameness in pigs with different body types or ways of walking, like pregnant sows. Some of the final challenges have to do with the data. First, PLF systems will be sending data either to central locations on farm or off farm for processing and storage. This means the farm needs internet connectivity to move the data from where it's collected to where it's processed, and then to the producer's phone or device where it'll be used. Another consideration as part of this data transfer to keep in mind is what type of data are being shared and who has access to it and who owns it. So considerations of privacy and data ownership need to be worked out from the start. Well, Madonna, what do you think? Have we set the stage well enough? Are we ready to turn this over to our panel of experts?
Oh, I think so, Janice. But first, we want to remind our audience to please put questions into the chat box. It doesn't have to be questions. Maybe you have an idea. So please share that. Or if you want to, you can speak up during the discussion sessions that will happen later.
Well, thanks, Janice and Madonna. That was a great overview, and I think you really emphasized a critical feature of precision technologies, that they're designed to help farmers respond at the level of the individual animal. Now we're going to zoom over to the University of Wisconsin and meet Dr. Zhao Doria. Zhao is going to describe work by his lab using computer vision systems to improve management decisions in cattle. Zhao?
Hello, everyone. Today we will talk a little bit about how to use computer vision systems to improve decisions in livestock operations. And the focus of our presentation will be more on the dairy side, what's the applications we are developing and planning to implement in commercial farms. And we will present a little of what we're doing in our research here. So before we dive into the computer vision and the precision livestock farming, the sensor technology, it's very important to remember why we are doing this. And the dairy farm and a feedlot, a beef cattle feedlot operation, they are complex systems because the amount of information that it's used and collected every day, it's not small. And the overall goal that we have of collecting those variables is to have optimized decisions. That's what we want to do at the end of the day. We collect data related to nutrition, to genetics, to economics, health, and at the end of the day, what we want to do is have optimized decision, either if it's related to nutrition or if it's related to repro. But what we want to do is be precise in how we are deciding things in our operation, right? And if we look to those pictures here, we can see the complexity of the system that I'm talking about, right? So we have cows that are eating, so we need to be being in and monitoring the feed and how feed is being delivered to those cows. you need to pay attention to the body condition score and the comfort and the well-being of those animals, on the water, on the ventilation and the housing as a whole. So those images can tell a lot about what's going on dairy operation. And that's what the computer vision want to do in an automated way. It's looking to the scene, looking to the dairy barn, and with a single image, you can assess what's happening in terms of animal well-being and behavior and nutrition and so on. So that's why, and the motivation that we are implementing computer visions are using that technology to help us on the management standpoint. But the data that we have most of the time from the livestock operation, they are sparse and they are noise. And what I mean by this is that the information we collect today, and then the next information of the same point or the same topic, only in a month, will create a sparse measurements. And those sparse measurements can preclude us to develop good analytics and have this precise decision or optimized decision that we want to have in an efficient way. So here's just a quick example about how a sparse measurement is present in our operations, in the livestock operations. And the example that I picked here is a feed bunk management, right? So usually in a beef cattle feedlot operation or in a dairy, we go in the morning, we see the bunk, and sometimes the bunk are empty. The feed bunk are empty in the morning. And when we look at empty bunk, the question that comes is, this bunk was empty since an hour ago, right? Or 10 hours ago. How long that feed bunk was empty? And because we do not have technology to monitor that in real time, we take a decision based on a snapshot, based on what is happening at that exact moment. So here's just a quick example of two pens, pen 6 and pen 7, they are closed, and both are empty in the morning, 7 a.m., right? But if you, in those pens, we have cameras monitoring the feed bunk all the time. And if we look back, what happened the day before, we can see, for example, 4% of the time of pen 7 the day before was empty, while pen 6 the day before stayed 30% empty. So if I look in the morning and I take a decision based on the snapshot on the morning, I'm adjust the feed delivery in that day for pen 6 and pen 7, I will probably make a mistake because what I need to adjust for one pen is not what I need to adjust for another pen if I look at real-time data for the last day, the day before, right? So that's how important it is to have real-time measurement, and that's for all areas. That's for body condition, or that's for animal behavior. It's really important to have more data in terms of time series and real-time information to have better decisions. So what we are interested, it's something called high-throughput phenotyping. That's a little weird name in the animal production side, but it's very common in the genetics. And what this high-throughput phenotyping thing want to do is to collect animal level information as much as possible in a cheaper way and a precise way, okay? And the goal of collecting this high-throughput phenotyping information to my lab is to improve farm management decisions that is specifically related to animal nutrition and health. And when I talk about the animal level information, I'm talking about those variables here: animal identification, behavior, growth development through measurements of body weight, and so on, okay? And the way we are collecting that information is through technology. And there are several technologies that can be implemented to do this. I listed some that we are working from the research standpoint here in Wisconsin. That is the use of accelerometer or wearable sensors, computer visions and cameras. That's actually heavily most of the research that we develop, and infrared spectrometry too. So those sensors are very powerful and they can help us a lot to collect that animal level information. And we will be using these for farm management decision, but there is a huge opportunity to collaborate to collaborate with the geneticists because they'll be using those phenotypes for breeding programs. So that is a very good field to be developed and open for collaborations in that regard. So today we'll be talking about computer vision, more specifically cameras, and we'll be discussing 3 examples of application very related to animal identification, behavior, and growth development. Okay. So how we want to do this, right? We are talking about computer vision applications, and do we need to breed all of this from scratch? Do we need to invent all of those things? The answer is no. That those applications, they are being implemented in other fields, in other industries. We can see here autonomous car that is in the road of detecting the other cars and doing this in an automated way. And we have smart cities and retail and grocery stores using cameras to control what people are buying. So that is a framework, that is a field that is developed in that sense. So we do not need to reinvent the wheel. We can take advantage of other industries and bring a lot of good technology to our industry, the livestock industry. And when we think about computer vision systems being applied in animals, the first step and the first thing we need to think about it is how can we identify the animals, right? If I have cameras monitoring body condition score or body weight, before I predict that body condition score, I need to know which animal is that, right? What's the idea of that? And if we look through the US, what we have in the majority is the use of ear tags, right? Most of the time, not even RFID technology. But in the dairy side, probably we have a huge amount of RFID as a way to identify the animals. But the use of image has been very explored as an alternative, right? Because there is no way you can fraud or you can generate stress by animals. There is no human error when you have those images, and that has been explored by different groups, including our group. And we are very good to identify animals with different coat color pattern in the case of hostings, right? So we ran a trial, and we were able to identify in this pilot the animal based on the color of the coat color. The accuracy to identify that animal was very good, very impressive what the algorithm is doing here. The problem is so as we can identify the animals, so the question is, now what, right? I can have a very good prediction of animal based on the coat color, and what I can do having those identification of animals that are housed in group as those calves here. So by having that identification, I can, for example, know if an animal is going to the bank and how long the animal is spending in the bank. So I can collect information related to the feeding behavior and the time that the animal was spending eating and the duration of the meal and the size of the meal and so on, right? So here we have a little video that can show you how the system would work on those animals. And if we look to the accuracy to detect the visits on the bank, they're very high. Right? So now, if I have an animal that possibly gets sick or not eating, I can clearly see that pattern happening in the data as I have real-time information of which animal is going to visit the bank and how long the animal is spending. The problem is when we have animals with the same color, right? There is no coat color pattern that could differentiate the animals. So in the case of the jerseys, or for example, in the case of the black Angus, it is more complicated to use the image analysis to identify the animal. So what we are doing is, in this case, we are using the shape of the animal to identify the animal. So those images here, they are what we call point clouds, and that is describing the shape of the animal. But in using the shape and the biometry of that surface or of that shape, we are classifying the animals. And in this trial with 38 calves, we got an accuracy of 87%. 87% identify the individual animal based on the shape of the animal. Right? So that's pretty impressive and very powerful to be implemented in the field. Now, the animal can change shape. The question that arises is, how can we control for that? How precise the system will be as the animal changes the shape because the animal is growing, or because how it's mobilizing body fat, for example. So we use data from dairy calves that were growing, and we use to train the algorithms, data from week 1 and 2, and we use the image from week 3, 4, 5, and 6 to generate the prediction and see if the algorithm would be able to identify those calves, even in different stage of growth. And the accuracy stayed high in that short-term period, that short period of time. We need to understand better what would happen if we would have longer periods of growth and if the animal change too much. So when we lose the accuracy and we need more image. But still in these 6 weeks, the algorithm was able to identify the animal body shape. The number of images is something very important. As you increase the number of images in the data set, the accuracy of the identification also increases. So if we have few images of an animal, it's very possible that your prediction will be bad, and that's something we need. Now that we can identify the animals, we can also do other things. And one thing that we are interested from the computer vision standpoint is monitor how the growth is happening and how is the growth developing of individual animals. And the reason we are studying this specifically is to understand the growth and use that growth information to make better heifer replacements in the dairy herd. Okay, how can we associate that with production and how this can be used as a strategic way to do the heifer replacement? So we run a trial with dairy calves, which we collect the body weight and the image, the 3D image of those animals. And we develop an algorithm that can segment and exclude all that is not the animal on the image. We get all the best frames and we segment and only get the body without the head and without the tail. And we extract many features from that 3D image, okay? So we extract volume, area, length, extent, width, height, and we use those features to predict body weight. Right? So if we look to the association between volume, area, length, for example, and body weight, we can see a very strong association for the features extracted from the image and the body weight. So, and more important than using those features to predict body weight, it's the use of those features to understand how growth is happening. And an animal that is growing more in skeletal development compared to body fat, we can clearly see that in the differences in volume, in area, or in the height of a specific point along the body. So those biometric measurements are very important to monitor how they're growing. And the way we collect that information in commercial settings, it's in animals with the same color. In the case of this Nelore cattle, it's using RFID and the combination of the RFID with the cameras. So we have animals going to the water to drink water, and every time the animals approach the water, we read that animal, we take a picture of that animal, and we extract the biometrics that I just mentioned to measure body weight or to control or to monitor the biometric measurement of those animals. So the quality for the dairy calves that we have in terms of prediction, it's very good. The relationship between the predicted and observed is very high, and the error of prediction it's very low, and we think that will decrease even more as we add more data to our models. In this case, we had only 38 calves to train the models and 30 to validate the models. So with the experiments that we have with the beef and pigs, we have much larger data set, and consequently we have much better prediction too. So that's how we think that this can be improved. So now that we can identify the animals, and through the identification we can assess feeding behavior and also growth development, can we have more detailed information about the behavior? And that's something we're investigating too. And the answer is yes, we can. We are trying to evaluate if the animal is standing, it's lying down, it's drinking water, it's eating grain, and the accuracy to identify those activities, they are super high, they are very good. And these will allow us to have a more detailed information of the behavior. And by using that in a time series, in a real-time assessment, we can pick a small difference if the animal changes behavior. As I have images here, for example, coming every 5 seconds, every 5 seconds, I know if the animal is standing, lying, or drinking water. And if the animal drop 2% of standing time today and 5% next day and 10% next other day, we can possibly pick that small change quickly than if we would using visual observations, for example. Okay. So combining that behavior recognition and the identification, we can cross that information, and for each animal, we can have information about if the animal is drinking, standing, and then we can control those animals very well. Okay. So this is very powerful, and the change that the precision that we can see on those measurements can definitely help us to identify health issues, for example, right? And that's the goal with those behaviors prediction is how can we early detect animal that will get sick and take an action based on that information and make our system much better. So our research group, it's composed by people that are from different backgrounds. We have an animal scientist, engineer, computer scientist, and those guys were developing some of that technology, and they also develop implementing the technology. And we have a group working heavily on those development and in the analytics that goes behind that development. We have another very common type of lab in the animal science department. We have a little bit of electronics and camera work, and that's necessary for us to measure the phenotypes that we have in interest. I would like to thank the funding agencies, I mean, the USDA, NIFA, Wisconsin grant from Microsoft for the dairy calves, WRF, which is the office that takes care of the patents that we have through this computer vision application, and the other partners too. Okay. Yep. Thank you. If you have any questions, I'll be glad to answer them.
Well, thank you, Zhao. Computer vision coupled with the type of machine learning you described today to track individual animals is going to provide farmers with an incredibly powerful set of tools, I think. Now we're going to visit Dr. Tammy Brown Brandel at University of Nebraska, who will be joined, I think, this morning by Dr. Benjamin again, to learn about recent work on precision technologies in swine production. Tammy, are you there?
Hi, I'm Madonna Benjamin. I'm a swine extension veterinarian and assistant professor at Michigan State University. And I'm really pleased to be a part of precision livestock applications in swine.
Hello, I'm Tammy Brown Brandel. I'm a professor at the University of Nebraska in Lincoln, and my title is Precision Livestock Engineer, and I'm very honored to be able to speak to you today about my research in this area. Madonna and I are here to talk to you about precision livestock farming applications in swine production. both on the research side and on the production side. The continuous collection of data from these sensors allow us to have a new view of animals within their production system. However, these data are much more difficult to interpret than standard production data. While we'll provide you a few examples as we give our presentation today, we will highlight the need for both professionals in many different areas and producers to work together so that the data is correctly interpreted and can provide needed information back to the producers. As a producer walks through the pen, we can understand why it is difficult to identify individual animals for illness, lameness, signs of aggression, and other management things. In order to aid producers, one method of capturing information is using radio frequency identification, or RFID. There are several different types of RFID. You are likely more familiar with the low frequency passive RFID tags. These are commonly used in electronic sow feeders in sow barns. While they don't require batteries and are lightweight, they're relatively inexpensive, $2 to $3 a piece. However, they have a very short read range, from a few inches to 3 feet. The benefit of not having a battery is they have almost an unlimited life. Active tags, we'll talk about later, are more commonly used in research. However, they have some advantages of precise animal tracking and long-distance reads. But currently, they cost around $40 a tag. These are the same tags that are used in manufacturing, like for tractor inventory. And the dairy industry also is starting to use these in a system called SmartBow. The first thing we did was we developed a system to track feeding behavior in standard feeders in a pen of about 40 pigs. This graph shows feeding behavior, or total time spent at the feeder for each individual pig over a 24-hour period, from about 8 weeks of age when they entered the facility until they left the facility after they reached slaughter weight. This is called a data stream. However, this information is not useful to anybody in this form, so let's start processing the data. If we average all of the pigs together, this gives us a nice view of the building or the pen information from all of these pigs. When we start looking at the data in different lights, we learn more about pigs than we ever did before. In the past, feeder space was determined by the average weight gain in a group environment. However, using this individual data, we can see that within 1 week, slower growing pigs spend less time at the feeder than fast growing pigs. While that isn't surprising, it is interesting that when the fast-growing pigs reach market weight and are removed from the pen, the slower-growing pigs double the time at the feeder. This is really important because it really shows some social interaction in our animals we've never got to see before. Dr. Steibel will later talk about the impacts that genetics play in this data and how this data can impact genetic selection.
So, Tammy, this is an industry disruptor. I mean, as you pointed out, we typically measure weight gain, but if there's a correlation between weight gain and time at the feeder, individual pig time at the feeder, this can do so much for the industry as far as PLF and monitoring, and whether it's the location in the pen or feeder design. I think this is a disruptor.
Absolutely. Feeding behavior is very important, more important than weight gain, because it changes very rapidly. And we can see those changes. If we have a method of seeing that, then we can really understand what's happening in the pen on a day-to-day or maybe even on an hour-by-hour basis. Now we start looking at the uses of the individual animal data. This data can be used to identify pigs that aren't eating as expected. Such disruptions in time spent eating, like in this pig, might show illnesses or other things that are happening in the pen. The raw data in this graph is shown as the black dotted line. The red line is the model prediction. When those two do not match and the difference is large enough, an alarm can be given to the producer. We are creating this tool to assist caregivers or caretakers in identifying sick animals. In this case, the tool was able to detect sickness in this animal 4 days before human observation. Because the data stream is 24/7, it really gives us a nice view of what's happening.
And as a practitioner and looking at your model, I can see an opportunity for demonstrating one, identification, two, the decision on when to treat, and three, to see if there's actual response and determinant of return to investment. For example, I might suggest to the farm through a standard operating procedure that they identify the pig at alarm 1 and at alarm 2 that they treat the animal.
This system gives you a nice view of the response after this pig was treated, and the pig was treated on the green triangle here. You can see how quickly that animal returns to a normal time at the feeder per day. When we look beyond time spent eating and start looking at pigs how they utilize space within the pen, we might want to look at active RFID. This gives us a precise way to track animals through the pen. So we can put these tags on individual animals in the pen, and then we can track them as they walk around the pen. This gives you a view of 4 individual pigs in a group of 40 over just a 24-hour period.
Does each color represent a different pig, Tammy?
Each color is an individual pig, yes. We had actually instrumented 24 pigs in this pen, but you can't see it if we put more than 4 on a graph. Do you see patterns in these movements? Where do you think the feeders are located? Where do you think the drinkers are located? So here's the same 4 pigs, the same data, only I've overlaid the pen layout. So you can see the yellow rectangle is the feeder. The 4 little blue squares here are the drinkers. The beige oval is the dunging area. And the light blue rectangle is the sprinkle cooled area for the pen. What do you think the red triangle represents? Put your answer in the chat box. And we'll come back to this at the end of our presentation. We're going to switch over and start to show you how we can apply PLF data streams to the farrowing house. This is a standard farrowing house, and this is where we are collecting our data. As in any good design problem, we need to start with problem identification. So our problem is we have high pre-weaning mortality. So our question as engineers are, why is that? And one of the things we've come to are the crates too small? They were originally designed in the 1970s, late 1970s or early 1980s. Between then and now, our sows have become quite a bit larger, and we have increased our litter size. So the first thing we really wanted to focus on is space quantity. So this is a traditional crate. This is a 5-foot wide crate by a 7-foot long crate. She has about 24 inches of space, the sow does. The newer crates are 6 foot by 8 foot. The question is, if we give extra space to the sow and the piglets, do we allocate that space only to the piglets, shown like in this green crate? Or do we divide that extra space between the sow and the piglet, shown here in the blue? Now, how do you think increasing crate size impacted production? Unfortunately, not at all. There were no differences in mortality, overlays, or piglet weight gain. We also looked at providing 1 and 2 heat lamps, but there were no production differences at all.
So are you saying that the small crates are as productive as the large crates? There's no difference? between large crates and small crates?
Well, if you only look at the production numbers, that is what the study would say. However, there are several other things that I believe that we should consider, like sow and piglet well-being, comfort, and welfare.
Well, that's all well and good, Tammy, to talk about welfare, but how are we going to demonstrate return to investment to our producers and the benefit for all?
Well, that's where PLF really plays an important part here. Let me tell you about depth cameras and how we can capture the information throughout the farrowing cycle, not just at the beginning and the end points. First, I want to tell you about a depth camera and what a depth camera is. A depth camera is a low-cost camera, but instead of giving you colors, it gives you an array of numbers that are distance from the camera to each pixel in the whole image. So this is just an example. So if we plotted that out, it would look like this. So the floor would be the farthest away and the sow would be the closest to you. So to make that look real, we invert the image. So here's the image of, this would be our pretend sow. And this would be the floor around here. So as you can see, we have a nice contour on the back of the sow, and that really helps us determine posture changes. So here's the installation of our system. We have a depth camera placed over the top of every single farrowing crate in one farrowing barn. So that means we have 60 depth sensing cameras. They are located here, and 60 mini computers with a little monitor. And they are recording images every few seconds. And those images are both digital images, so you can see what's happening, and depth images, so you can really understand some posture changes. Those are all stored in a special drive over Ethernet connection. Here are the images, and that's how they look like after they are collected. So this sow is setting. And it's really helpful if you look at the depth image, because you can see her head is a light or darker blue and her bottom is yellow. And that says that her head is closer to the camera than her bottom is. So she is for sure setting in this picture. Okay, so the results of our posture changes really indicated we got some differences in time spent laying down, standing, and setting. So sows in wider crates spent more time laying down than sows in narrow crates. The greatest difference was on the first day after the piglets were born. The sows in wider crates laid down almost an hour more. That can have a real impact on production, even though we didn't see it. It's very interesting when we start looking at transition postures like setting, because those animals go from laying down to setting and then to standing. The sows in the wider crates spent less time setting than sows in either of the two narrower crates. In order to interpret this data, we really needed a little bit more information. We measured the space the sow needed when she went to stand up or lay down in an open pen. This gives us an idea, not maybe how much she needs in a crate, but it gives us an idea of how much space she would use in an open pen and helps guide our decisions when we go to a crate. Okay, so what we found out is from laying down to standing up, a sow used 2 square meters or almost 20 square feet of space. Your typical farrowing stall, the standard ones that were designed in the early 1980s, provide 1.3 square meters or around 14 square foot. So they really need some extra space to go from lying to standing, which is probably why those narrow crates, the sow spends more time setting, because she's just trying to position her body to stand up. When she goes from standing to lying down, she used about 16 square feet of space, which is much closer to our standard crates. The other thing we found with those transitional postures is kneeling. And kneeling wasn't maybe necessarily a good indicator of whether they have enough space or not, but really showed us some interesting stuff on mothering ability. Sows that were better mothers spent time in this kneeling posture. And what kneeling is when they go from standing, then they put their front 2 feet down and their back end is up, and then they slowly roll over. So they go down to a kneeling posture. So sows that lost 0 piglets had kneeling behavior, or we were able to capture kneeling behavior. Sows that lost several piglets in their litter had 0 images that we were able to capture them in the kneeling posture, which means those transitions for them were very, very quick.
So Tammy, that's another game changer, because if we think about it, when we assess animals for genetics, we look at leg composition and udder length and other aspects. I don't think we're looking at athleticism, and that's what kneeling is.
Right. And you know, sows that have feet injuries aren't going to be able to do that kneeling posture very easily, right? They're going to lay down quickly so they don't put pressure on their feet. This is a way that we can start to monitor that. So we evaluated these different sizes of crates. And so after we got done, we thought maybe we should stop and reevaluate this. And as we look at these crates, they all have a very long, narrow piglet area on either side of the sow, and the sow is in the middle, right? However, when you look at piglets in a crate, they much prefer to lay in a circle. Piglets are very, very social, and they like to touch each other. Even if they are warm or hot, they will still lay and touch each other. Very rarely do you see piglets lay in a rectangle, much more likely to lay in a circle. So the other thing to know is that sows like to be, and producers know this as well, sows really like to be very cool, right? And so they would like to be at about 60 degrees Fahrenheit, where piglets are comfortable more closer to that 85, 90 degree Fahrenheit. That's why we provide a heat lamp for the piglets to provide that supplemental heat. So when we look at how those supplemental heat is going to impact our crates, we really look at, this is taken with a thermal image. So the dark red shows the warmest, and the blue and the purple show the coolest. So if we do our standard crate here, you can see how much temperature, how much that heat lamp is impacting the sow space. So what happens if we redesign these areas and allow the piglets more space, at least on one side? So we offset the crate here. This side here is the same spacing as our 5x7 crate, and we just provided all the extra space on one side. But you can see how much less the heat lamp impacts the sow space. Then the other crate that we really wanted to look at was a diagonal crate. And here's a diagonal crate creating 2 triangles of space. And you can see how that heat lamp doesn't impact the sow space at all.
So looking at this, Tammy, if we had an interface from the PLF that showed not just the piglets, but those barriers, kind of the heat zones and the cool zones, it also provides for the producer an opportunity to use rheostats or dimmer switches based on these sensors, saving money and saving pigs.
Absolutely. Here you can see how, and we're just starting this study, but you can see this is a standard crate and how the piglets are laying in that sow area. And here's the offset crate. The piglets are still forming their circle, but they really are staying out of that sow area. Here's our diagonal crate, and you can see our piglets are forming a triangle instead of a circle, but they're really outside of the sow area. So in conclusion, I believe PLF will help producers by starting to answer some of their challenges that they're facing today. So with thermal environment, we can then see how that thermal environment's impacting the sow and the piglets. With being able to detect individual animals in a pen, you can pinpoint that not only which animals receive antibiotics, but the timing of that antibiotic use. With the data, we can then see animal well-being and how different changes we are making are really impacting sow well-being or animal well-being. And I think with this, we can also look at labor shortages and really help our producers be more time efficient. So our final slide today is to give you the answer. What do you think that red triangle represents? If you would believe it, that red triangle is 2 chains providing enrichment for those pigs. Look at how much time they spent playing with those chains.
Thank you, Madonna and Tammy. And I did suspect that was an enrichment device attracting those pigs, either that or someone standing there with some marshmallows. Now, before we move on to our first Q&A session, we're going to do a quick spot poll and ask all of you to weigh in on 2 questions around precision farming. We're interested really in your initial thoughts on these topics. So we'll leave each of the questions up for just 10 or 15 seconds. And the first question is, what is the most pressing issue precision technology could address if you adopted it on your farm? And the options are to avoid labor shortages, A, B, increase performance and production, C, improve welfare and health, and D, other. So if you'll take just a little bit of time to answer that, we will have results. We will have results in a few minutes, I think. Oh, we got them now. Increased performance in production. Interesting. Okay, and now we'll move to the second spot poll question. Do you use other types of technology than those discussed? Just a real quick one. Yes, no, I don't use any precision technologies currently, but I'm considering it, or not applicable. And that'll take just, I think, about 15 or 20 seconds. If you'll weigh in on that quickly. Okay, well, Megan is calculating those, and it might just, oh, there they are already, not applicable. Okay, and then I don't use any PLF technologies, but I'm considering. So we really have just a few using some of these technologies already. So good, interesting. Thanks to all of you for weighing in on that. Next, we're going to spend a few minutes and address questions that you may have. And there have been a few that have come in that have been answered in real time, just require short answers. But a couple of them that came in, including one by iPhone here, was very interesting. And so I think we'll take just a minute and look at that. The question, and I'm going to paraphrase here, is that PLF technology looks expensive and like it might require a computer, IT, or engineering degree to make it work on my farm. Is this a misperception? How costly and complex is it today? And do you expect the cost to come down in the future? And Tomas, maybe I think this would be a good one for you to answer.
Yeah.
Are you there?
Yeah, I'm here. Thanks, Dave. Yeah, it's a very interesting question. First of all, I think we will for sure see in the future the cost of these technologies come down. But the thing is, it's all about the business model for the system. And that's why it's key that researchers and technology providers and farmers work together to develop them. Like if you look at a mobile phone, there's a lot of very expensive tech in that mobile phone, but because we pay a subscription for that mobile phone, we don't really feel the price of paying for the technology. And I think that's the step that really needs to be done. Researchers, technology providers, and farmers need to work together to decide what the business model is for the solution, because we know that the technology is actually there. It's a way of getting it onto the farm. That's the next step. And I see it's really about an interaction of maybe at least two business models. The business model of the farmer, and typically he wants to improve his efficiency, and we see that from the poll. That's number one, right? And then there's a business model of the technology farmer or provider himself, and they need to think about how can they support the farmer's model, but also get him to pay, or else get some other stakeholder to pay. And that's where another stakeholder can come in. For instance, a supplier of medication to the farm, or a supplier of feed. So a technology provider can actually interact with their business model and the business model of the farmer, and the farmer can then deploy the solution far cheaper than he would be expected to if it was just to support his production, but in fact he's also generating valuable data for another stakeholder. So they're paying the price for that. And these kind of solutions is what we need to look forward to in the future to ensure that the technology hits the market.
Thank you, Tomas. Second question also came in iPhone. Which among the current available PLF technologies provide the most robust benefits, and how solid are the vendors' data packages supporting them? Maybe this is a good question for Madonna and Tammy.
Well, I have some thoughts, and I'm interested in Tammy's thoughts as well. I'm thinking about, from an application perspective, what we're already good at and what we're not good at. We're not good at providing subjective information. So if PLF can, if and when it provides quantitative information, then that can then feed back into our benchmarking programs so that we have true key production indicators, and that perhaps, you know, some of the indicators that'll come up, for example, access to feeder space, maybe that becomes a key production indicator instead of days on feed.
Tammy, anything to add to that?
Yeah, so I think as we learn more about these technologies, I think we can then tie some of these behaviors that we're learning about back to production numbers. We aren't quite there yet. But we are working on it.
Thank you. We've had another question come in, this one online. Maybe this is a good one for Janice. PLF can help with labor shortage. Do you think it can also help with employee satisfaction and increase retention or decrease employee turnover? And if so, how? Very good question.
So I think one thing that PLF might help us do is free up people from some of the things that are kind of the drudgery tasks, right? So things where you're spending a lot of time counting or marking animals or things like that. And so instead of perhaps engaging in some of those repetitive kind of onerous labor intensive activities over and over again, now perhaps people can turn their time to other tasks like working with the sick animals and treating them, doing things that are maybe more related to kind of individual care or to kind of higher level problem solving that let people put their time and their minds to good use. So that may be a way of doing it. And if people are also able to become competent in using the technology, you know, maybe you have some people that are trained to troubleshoot it and fix it. Other people maybe that can tweak the programming to give you exactly what you want on the farm. So you may also attract people who are really interested in that tech side of it to come and work on the farm, and they can kind of marry, maybe their desire to have careers in agriculture with animals, but also kind of this tech savvy approach that they'd like to take to it. So it might appeal to, perhaps some of the younger generation or some of the computer tinkery minded among us who like those aspects of things.
Thank you, Janice. We've got several other questions that have come in that we will get back to later, but in the interest of time, I think we're going to need to push ahead here. Now we're going all the way across the pond to Leuven, Belgium, and try to patch in Thomas Norton. Thomas, I think you're on. And Thomas will describe some really cutting edge precision technologies for poultry production. Thomas?
Hello, everybody. My name is Thomas Norton. I'm an assistant professor at the Catholic University of Leuven. And my speciality is in precision livestock farming, and I lead a group focused on this field, working on many different species, ranging from poultry through pigs to even vultures. And today I'll speak about the applications and the work that we do in poultry production. So I'll just start a little bit quickly about what is precision livestock farming. It's all about this guy in the center. We want to support him in managing his farm. And it's not an easy job nowadays. So there is a lot of animals that he has to manage in order to generate a profit and to create a good livelihood. And therefore, he needs some help to manage these animals effectively. So we're looking towards what kind of technologies can support him. And there's a plethora of devices around at the moment. And yeah, we really want to make sure that he gets the right devices to support his production. Today, what I want to go through is some technologies that we have been developing in the research team, and yeah, some of them are still at research level, but also others are actually on the market and functioning. And I want to start with the incubation process and move through to the production process. So one of the major areas in the research team that has been there for roughly 20 years now is the modification of the environment around the egg during incubation, with the idea of trying to reduce the hatch window. In other words, the period of time it takes from the very first egg to hatch to the last egg to hatch, to reduce that time to make it a more efficient process. And we do that with a company called Peterson. And one of the interesting things is how to control this environment in the incubator, because these eggs are developing, the embryos in them are developing, and while the embryos are developing, they're producing heat. And then this drives heat loss, and yeah, the airflow and temperature is very difficult to control around the eggs because they're all exchanging heat with the air, and this creates this heterogeneous environment inside the incubator. And that was always a challenge, how to control the incubator. So the first idea was, okay, can we look to the eggs themselves to try and optimize the environment? And of course, the real problem there is you can't get into the egg because you don't want to break the egg, you want the embryo to grow. But how do you get a good proxy measurement then for the temperature of the egg? And one of the early experiments showed that you can get a good approximation with a little bit of modeling of the embryo temperature by measuring the eggshell temperature. So the eggshell temperature is actually a very good measure of the embryo temperature. And we did, the research team did work through the work of a postdoc at the time called Andre Brecht with Peterson to develop a system that was able to monitor the surface temperature of eggs that were sitting around this sensor. And then this was used to control the incubator. And here you can see that the eggshell temperature was used to control the environment around around the eggshell, and it was able to control it very well. So in the first 10 days until the egg started to produce heat itself, the control was to within 0.02 degrees, so it's really fantastic control. But as soon as the egg begins to produce heat, of course, it becomes more challenging because some eggs are developing a little bit faster than others. But even then, using the eggshell temperature as a way to control the environment was, came in with a reasonable 0.3 temperature difference in terms of the air around the egg and the eggshell itself. So it was actually a reasonable way to control the environment. But that was a basic control, and what we like to do is try and build on top of this. And what we asked the question about in the research team was, okay, so you have this eggshell temperature, we know it. Can we get the stage of development of the embryo inside the egg using this eggshell temperature? So what we did, and this was led by the postdoc in the team, he's still there now, working on this in this same field. And what the experiment he devised was, okay, if we increase the temperature inside the incubator by 1 degree for a period of 2 hours every day while the embryo is developing, we will see a response in the eggshell temperature. But that response will change as a function of the development of the embryo. So let's look to this and see, does it tell us about how well that embryo is developing within the egg? And these are the series of step changes in temperature that was applied in the incubator. And there was modeling done to this. And in the first 10 days, typically this response was received in terms of the eggshell temperature as a function of that change in incubation temperature. So it's quite straightforward model, but the shape of this model was the same, but the magnitude and slope changed, and this gave some insight as to how the contents of the egg were changing as a function of time. So the contents of the egg kind of give an idea of how the resistance of the embryo to the heat exchange that was happening. But the interesting thing happened after day 13, and this is really when the embryo begins to develop and produce heat itself. There was this sharp kick at the beginning of the step, and this is what's called a second order response, and this is actually the embryo reacting to the change in temperature. And this was a new effect, and this was modeled. And by modeling this reactive effect, which is in fact a thermoregulation, it was possible to get information on the stages of the embryo. So what was interesting was, by applying this temperature sensor, it was possible to stage the embryo of the embryo development within the egg, which is very interesting for the company in order to optimize their control of the incubator. I'll move on to the second idea for this talk, which is using PLF systems for early warning in broiler houses. So here, what we're interested in is to look to the movement of the birds within the broiler house during the grow-out phase, and use this information to alert farmers whether there is a problem with the flock or not. And in other words, we're using the animal as a sensor here. The animal is a sensor. So we should expect a kind of uniform distribution of birds throughout the floor of the building. But of course, when there's problems with climate, the climate control, with lighting, with drinker lines, feeder lines, this uniform distribution breaks down, and you start to see birds congregating together at different areas of the house. Of course, wet litter is also a big factor that often causes this. And what the team have tried to do is to use the data coming from the camera to look to the distribution. So in other words, how well the birds are distributed in the building, and to model this as a function of time. So this model, it looks like taking the average of the noisy time series, but this is actually done in real time. So it takes some history, and then it makes a little bit of a prediction for the next light period. And then the measurements that you take are compared with that to see, are these measurements expected at this stage of the cycle or not? And this is the kind of alerts that this kind of system can give you. So for instance, here we have measurements in this graph of the distribution. And what happens is at every light cycle, the distribution is compared to the previous distribution. And if it's outside of, if it's 25% or more different than the previous distribution, then an alarm is raised. And here is an example of that. Here you see a very nice uniformly distributed flock. So the graph is green. But then when it comes to here, you see that the distribution is outside 25% of the previous value. So therefore, it indicates a problem. And looking to the feeder line, there was a problem. The birds were congregating in the house in a non-uniform way. And it turned out there was a problem with the feeder line. So very simple measures to give an indication of a problem, using the animal as a sensor. And always the key with this is to try and look to what the farmer is logging in his logbook and see if we can get more accurate information on what happens. And in the previous projects that we've done, our PhD student who's finishing his PhD, Alberto Fernandez, he found that at least 95% of the times when there was an alarm, there was something problem, like it was like a feeding problem, a water supply problem, a climate control problem. There always seemed to be some issue driving that. So there was, it's a valid way of monitoring a problem in the flock. One of the key challenges with it is it's not specific enough. And that was something that we started to think a little bit more, and we wanted to extend the functionality of the system. And we're taking it further in the current project. It's the Smart Broiler Initiative that's funded by McDonald's. We've a project running in partnership with Big Dutchman and a number of Danish partners. And there we're aiming to take forward the developments that we made in our in the dynamic broiler monitoring work that we've already done. Okay, so the last part of the presentation is looking to the production monitoring of the chicken. And here I give two examples, one of which is on the market already. And this is the monitoring of the weighing of the broilers. And this is a process that is on the market. Many people already implemented, and it is this. So this weighing system, the birds jump onto the weighing system, and the weight of the bird after that jump is then estimated. And the work here was to try and improve the accuracy, because these things run off a load cell. A load cell has typically an accuracy of plus or minus 1 gram. But the reality is that when these birds jump onto the weigher, some of them will hang off with one leg, like this one here. Some of them will be pecking, which will cause error. Some of them will be walking over. And yeah, typically, it's, you can say only about 25% of the birds are in a nice position to get an accurate weight. So what does this result in? Well, it causes errors. It causes errors in your estimation. And of course, if you link this also to the fact that towards the end of the cycle, the larger birds are too lazy even to jump on the thing, your errors are increased. So the work, it's very practical work that was done in the research team was, again, working with FANCOM to try and improve the accuracy of these scales, because the scales at the time of this work had some predefined statistical curves that were resulted in weights that were plus or minus 240 grams in error. So they really needed to be refined. And the idea again was a little bit like what I showed with the monitoring of the distribution of birds. So it's basically looking to the main weights that are being captured by the weighing scale and predicting some limits, so some plus or minus boundary of what you would accept as a measurement, and just accepting the measurements within this region. And again, this was using just some previous data to form some history and then making a prediction to the next time step and throwing away the data that fell outside those boundaries. And by doing that, it reduced the error quite significantly. So just by doing some updating of your estimations based on a previous history of monitored weights, you can actually reduce your error, and it's implemented in the current system of FANCOM. And this is the outcome of the system. You can see that these weights were just thrown away because they didn't add value. This weight's on the outside of the yellow lines. Okay, the very last one is quite an interesting idea. The idea was based around the fact, can we monitor the feed intake of broilers? By monitoring their feed intake and also monitoring their weight, we could get real-time estimations of feed conversion ratios, so it could be very interesting to do that. And the idea in the group at the time, and this was work done by Dr. Arda Adin, the idea in the group was to try and measure the pecking of the chicken while she ate her food. So basically, in this short video here, on the base of the red tray, there is a contact microphone, and that's measuring the sound each time the bird pecks at that tray. So the bird is pecking there. Basically, the sound of that pecking is captured. And there was a lot of experiments done. It wasn't just with one chicken, there was more experiments done with up to 12 chickens, in fact. And in that case, when there was 12 chickens, there was a camera counting the number of chickens at the tray at any one time. So it was possible to average the measurements to a chicken, individual chicken level. These are just the parameters of the experiment. And you can see there that there is a lot of, even though it was for 15 minutes or so of recording, there's still a lot of data that you need to go through and manage when you're trying to filter out these sounds that are not relevant, for instance. And this is some of the filtering that was done. And just an example, yeah, here is the noisy data on top, and then this was processed and by filtering, and then eventually you can get to a point where you just receive as an output the peckings. So every time the bird is actually pecking that tray. So this again is the sound, the original sound. You can hear everything in the background. It was in a lab, but still you can hear the ventilator, for instance, and that contaminates the noise. But this is the filtered sound. and the filtered sound, you can clearly distinguish those peckings. So that, and then by counting those peckings and relating it to the weight loss of the tray over time, it becomes possible to estimate the feed consumption or feed intake of the bird. So this is just showing the accuracy of the algorithm itself. It was 93% accurate when compared to the labeled data. And in the end, the model was quite accurate. So it followed quite well the actual feed intake. So the predicted and the accurate, the predicted and measured feed intake were quite accurate. What else? The other thing it shows, it was very interesting thing, was that it didn't matter if there was one chicken or 12 chickens on a per pecking level. The amount of feed intake that was taken in on each peck was more or less stable. So you can see that it didn't deviate so much from measurement to measurement. So it just shows that this is a method that can be quite stable. Yeah, because 0.025 grams, if it's stable as a function of the number of birds, then yeah, you can use it potentially reliably in a more extended scaled up system. So it's interesting. Maybe it has a future. We need to work with companies to try and realize that, of course. But there's still some things that we need to think about. So often questions I receive different talks and from students is PLF driving farming towards greater levels of industrialization? And I often just say things like this, you know, look to the consumer demand for fast food. It's growing, it's still growing. And it's the consumer that's driving industrialization. It's not really the technology. The technology is supporting the farmer to meet the needs of the consumer. But I do believe that we can also be part of a system rethink. We can use the PLF systems to actually measure changes we make on the farm and how effective these changes are. For instance, if we move towards a more welfare-friendly system, is it really welfare-friendly, or is it not what we perceive it to be? And PLF can measure objectively this kind of information. And another question is, will it ever make money for the farmer? I think what farmers don't want is to be faced with a situation like this, where they have so many different things coming, devices on the farm, and so many different data sources that they need to deal with and manage, that in fact all their time is given just looking at these data sets when they don't want to be busy with this. And it means that we need to work with the farmer to understand what they want. We also need to work together with the industry to be able to bring that kind of solution to the farmer, and work with different disciplines. Engineers will design systems for engineers. So we need to really work together with the different disciplines and the farmers to make sure that the solution meets these needs. Okay, so I'd like to thank you for your attention, and if there's questions, I'm happy to take them.
Well, thank you, Tomas. No wonder those birds are growing so fast. If my math is right, those broilers peck at about 1.5 times per second, which is amazing. For our final presentation this morning, we're going to come back to Michigan State University to the lab of Dr. Juan Steibel. Juan is looking even further into the future of precision farming and will describe how the huge data sets generated by it might be used to help address a lot of challenges that farmers and researchers face as they look for new ways to improve the health and well-being of animals. Juan?
Hello, everyone. My name is Juan Steibel. I am an associate professor in the departments of animal science and fisheries and wildlife at Michigan State University. My my main research interest is in the area of quantitative genetics and genomics, specifically applied to pig breeding. But through that interest, I've recently been working on precision livestock farming, and especially collaborating and interacting with colleagues that have precision livestock farming as their main area of work and research. Many of them, if not all of them, have been presenters today in the sessions. And so I will be offering a presentation on the added value of precision livestock farming data sets, and also making a summary of the presentations. In the talks that we listened to today, we saw that precision livestock farming system usually record data from multiple sensors. And then those sensors could be, for example, wearable sensors such as RFIDs or accelerometers. They could be remote sensors such as microphones and cameras. But whatever those sensors are, the amount of raw data that they collect, it's usually enormous. And it's virtually impossible to store all the raw data and keep it. And so the solutions that are proposed, that were proposed today, was to analyze those data on the fly, real time, using automatic algorithms, and produce what I call usable or processed data, which are simpler summaries, usually in the form of flags or indicators that can be used by the animal caretaker or the farmer to implement management decisions on the fly at real time. And from the presentations today, I think now we have a very good idea of what is the value in using the data in that way. But also, what I want to call your attention to today is the fact that an enormous amount of data is actually not used, and it has to be deleted. Even the processed data, the flags, the management flags, sometimes are not kept because there is no reason for that once the management decision was made, and those have to be discarded. If we were to keep all of them for no reason, we would quickly run into storage problems and other issues for nothing, basically. So what I want to talk about today is what are the possible uses for the raw and the processed data that is generated by precision livestock farming systems that would have an added value beyond and above any management decision that was already made using them. Before going into those specific uses, or some of those, I want to discuss or introduce this idea of the novelty behind the data recorded using precision livestock farming systems. From many of the presentations today, we observe that now we have the potential of recording novel traits that were or are extremely hard to record using the classic technology. And for instance, today we saw the case of monitoring pig feeding behavior using RFID tags or using computer vision. Similar idea also was presented for monitoring the feeding behavior of cattle, and also a very innovative idea was presented using sound recordings to monitor the feeding behavior of poultry. So feeding behavior in this case, that is directly correlated, as was shown in the presentations throughout the day, to feed intake, and then that also relates to feed conversion efficiency. Those are traits that are extremely hard to measure, and they are usually not recorded in commercial farms. Well, now with precision livestock farming systems, we have the opportunity to collect those. But also, in addition to those novel traits, we also saw that these precision livestock farming systems are able to collect data from, I would say, classical or common traits that are routinely measured in farms, such as, for instance, weight gains and things like that. But they can be collected in a high throughput way. So they can be collected in real time in a continuous manner. For instance, we can use images. We saw the presentation of using images from pigs and from cattle to estimate the live weight. Now, instead of having to walk the animal to a scale every time we want to measure the weight, the live weight, We can just take a picture or wait for the animal to cross in front of a camera. The camera automatically takes a picture and records that. And it can do that on a continuous basis. And now we have a classical trait that is recorded in a massive number of animals under normal production conditions and in commercial farms. Then today I want to talk about possible uses of this data collected in this manner, whether it's novel data or is data that we are already collecting, but now collected in an automatic and high throughput way. In which areas of livestock production system we could use them beyond the intended use of these data sets, which is for making management decisions. So I will be talking about incorporating those data sets into genetic evaluations, into welfare assessment, and on-farm research or on-farm product testing. Let's take a look on each one of those. In this slide, I'm presenting a timeline since the time a bull calf is born until the time that the first crop of his daughters have finished closed lactation. And by this timeline of around 58 months, now we have enough information to reliably evaluate the genetic merit of the bull calf. Now, as you can imagine, and many of you already know because probably you work with this, this is a very lengthy process, is time-consuming, is expensive, is justified because the value of the animal that is subject to the selection decision is a very large value. So the idea now is that, of course, with precision livestock, we won't be able to change this timeline. We won't be able to shorten it. But what we can do now is to start to incorporate traits and measure the traits that go into this genetic evaluation using sensors or using data collected from sensors used in precision livestock farming. In particular, to the classical traits that we are using right now in dairy genetic evaluations, such as milk yield, component yield, and type traits. We could also incorporate other traits such as feed efficiency, feeding behavior, etc. And moreover, we could measure the classical traits in a more automated way and in a very large number of animals. In addition to that, what I find that this is very promising for animal breeding and for animal breeders is the fact that now we can collect these phenotypes in an automated way in commercial animals. We are not restricted in working with elite animals, or for example, in the case of pig breeding in nucleus farms. Now we can go to production farms and start collecting this data in the actual environment in which the bull or the sire's genotype will be expressed in the progeny, which is the commercial animals. Today, for example, Dr. Doria from University of Wisconsin-Madison mentioned the key word that goes into this scheme from PLF into animal breeding, which is the word called phenotyping. Phenotyping is the measurement of classic and novel phenotypes or traits or variables in massive number of animals using automated technology. And that phenotyping can be done, for example, with some of the existing PLF technologies, provided that we keep some of those data streams and we link them appropriately. In fact, in order to get more relevant index of selections for the more relevant index of selection for the candidates of selection, in this case of this slide would be a bull, what we need to do is to link the phenotypes that were collected automatically on these commercial animals back to the genotype of the animal subject to selection. Also, Dr. Doria mentioned the idea and the need for individual animal identification. As long as we can identify and automatically identify animals in the commercial environment and attach a phenotypic measure to them, then we can propagate that measure back into the pedigree or the genome information that we have in the genetic evaluations and link that to the genetic merit of a candidate for selection. If that is challenging to do with images and with computer vision, perhaps we can consider the use of RFID tags that was presented by Dr. Brown-Brandl for pigs and for monitoring, for example, pig behavior and pig feeding behavior in particular. So regardless of how we do this, the key word here would be collecting massive number of phenotypes in commercial animals and then being able to link those to the lead animals being evaluated. Another area where PLF, precision livestock farming data streams could be used is in the area of welfare assessment. Currently, we have procedures for on-farm welfare assessment, which in general consist of looking at or observing certain variables and indicators on either groups of animals or on a limited number of individual animals that are not identified per se, but they are considered representative of the farm in which they are being raised. And of course, this is carried out in general by judges, which are experts and are well trained for doing this, so they can add their subjective criteria and assessment to these objective measurements and come up with a scoring system. And there is no doubt and no question about this, because through using this type of on-farm welfare assessment, we've seen enormous improvement in the welfare of livestock and also in the societal acceptance of the animal products that we are selling. However, with the adoption of precision livestock farming, we would be able to automate the collection of those measurements that are needed for the welfare assessment. We would be able to do this on a more continuous way. And what is interesting, and perhaps is more interesting to our consumers, the people who will be buying these animal products, is the fact that we are not limited to observing a set of animals which have to be accepted as representative of the rest. We could do this on every single animal. And then, as we need, we can compute summary records for a certain herd or for a certain farm. For instance, in the presentations that we saw today, we saw that a common interest for PLF applied in pigs, in cattle, and even in poultry was to monitor behavior. If we can automatically collect a massive number of behavioral records, and then experts could analyze those and come up with what is called like a quote-unquote normal behavior, then by monitoring the individual behavior of animals, we could see abnormal behaviors and use those as indicator of welfare. Dr. Sigford, for example, Dr. Jenny Sigford, who presented earlier today, is one of those experts from the animal welfare and behavior area that is currently working on designing welfare assessment schemes using precision livestock farming data. So this is a very promising area. And what I find promising about this area is the fact that will require that we connect consumers associations with producers associations, and we link them with the experts in the precision livestock farming, in the welfare assessment as well, so that together they can come up with the indicators that will be collected and transmitted from farm to consumers and used for maybe perhaps create differentiated products which are welfare certified, or for establishing new industry standards in terms of welfare that will be not only easily adopted, but also easily evaluated by the farmer, and the farmer could adjust those on the fly as they are producing these animal products. And the final thing I want to talk about is this idea of using precision livestock farming data sets for research, for testing products on farm. As many of you know, we traditional researchers are used to work with a controlled environment, whether that is a laboratory or maybe an experimental farm. We usually have a very limited sample size in terms of animals, very limited number of locations. Maybe it's just one farm, maybe it's only a few experimental farms, a small network of experimental farms. And we allocate treatments or the products that we want to compare to these experimental units that are, in general, the experimental unit is either an animal, a single animal, or a small group of animals to which we apply each treatment. And then we measure all sorts of variables, and we measure the response, and we try to come up with answers to our research question. Of course, this experimental design is optimal for inferring cause and effect. For instance, we can design an experiment in our MSU farm, MSU dairy farm. We could apply different diets and then measure the response from those dairy cows or heifers, and assess if a change in diet is causing a change in feeding behavior, which in turn is causing a change in performance, in milk yield, or whatever measure of performance we want to use. What this type of experimental design is usually not very good for is for measuring the actual effects in commercial farms. So we can determine if a change in diet causes a change in performance, but it's hard to determine exactly how much it will change in a commercial farm by looking at data from an experimental farm. The environment is controlled, it's not similar to the it's not exactly identical to those of commercial farms, and the number of animals is very used. Is very small. On the other side, as precision livestock farming is adopted, I would say worldwide, but maybe we can think of the US in our case, and it's adopted by many farms. If we are able to capture these data streams, the desired performance variable that we want to study, we could compare treatments applied at the whole farm level. In this case, the farm would become the experimental unit. So one farm applies one treatment, another farm applies another treatment. But, and of course, there will be a lot of confounding factors. There will be many things that are changed from farm to farm. But the fact that we can potentially treat each farm as an experimental unit and measure the response in thousands and thousands of farms, that would, in and of itself, provide a very good estimate of the average effect of the treatment. Now, maybe this is not good for inferring cause and effect. That still will have to be done under some control environment. But once we know that there is an effect, to estimate the size of the effect, this will be much more effective than trying to, let's say, run experiments in an experimental farm. For example, an interesting problem that we observed, that we saw today in the presentations, was by Dr. Tammy Brown-Brandl, and she used precision livestock farming technologies to assess the effect of heating element, the position of a heating element in farrowing crates, and how the animals responded to that, and to make decisions about the placement of those elements. Imagine if we could repeat this in thousands of farms. If this was a technology that was already adopted for management decisions within the farm, we could collect the data from thousands of farms, and not only collect the data on the heating element position, we could collect data, for example, on the type of heating element, the design, the brand, the characteristics, and maybe electricity consumption, things like that. Then we would be able to analyze all those data and group these farms into common practices and into common types of management regarding that particular heating element, and come up with a solution to increase the energy efficiency of farrowing rooms across the whole country. Perhaps we cannot narrow it down to a single configuration, treatment configuration that will be the best over all the farms, but we can narrow it down to a few options, and then within farm testing, using the same PLF, will help the farmer decide exactly what to do and which type of elements use. So this is just an example. It's more daydreaming on part, but it's just to show you the idea of how using data that's already collected for making a management decision within farm and linking it across farms, let's say from all over the US, we could come up with new technological solutions for management. So comparing treatments at the broad level of region or country. And the key, of course, the key for this to work is that we need to be able to access all the data. We need to be able to link the data records from each farm to other data sets which are collected on farm and off farm, and that will help us build the statistical models to dissect all these effects. In summary, I hope that by now I was able to convince you that there is value in extracting these data sets and using it for something other than making immediate management decisions. But what is most important, the most important message I want to convey is that for that to happen, for that value to be realized, we need to extract selected data and transmit it through the cloud so it can be reused. And Thomas Norton gave a presentation today where he mentioned that this is already being done by experts in precision livestock farming. So I hope that we can build on that and use the data for other purposes. In summary, for this field to move forward and for these ideas to move forward, I envision three big needs. One is an increased infrastructure for information technology for storage, transmission, and analysis. The other one is interdisciplinary input from engineers, from experts in genetics, in behavior, veterinarians, work together to realize this value. And finally, as it was mentioned by Janice Sigford, we will need to consider the social and legal consequences of sharing data that generates value. Who will own the data, how that sharing will be compensated, and so on and so forth. But with that, I want to thank everyone who attended this talk, and I'm available for answering questions.
Well, thank you, Juan. It really looks like some of those currently unused data sets could be mined to connect a lot of key variables that influence performance and welfare of livestock. Before we move on to our second and final Q&A session, we'd like to ask you to just take 30 seconds again and complete this in a second spot poll. First one, which PLF technology you heard about today intrigues you most? And we've got 4 options here. The first is 3D imaging to predict body weight in calves and monitor growth and development. Second is RFID tracking, individual feeding behavior for earlier identification and intervention of sick animals. Third would be monitoring individual chicken eggshell temperature to optimize incubators for embryo development. And then fourth, systems that combine multiple types of precision data to more efficiently link genetics to breeding programs. Those are four of the projects described today. There were several others, but these are ones that we're interested in data on right now. So take 10 seconds on that one. And then Dave, while those numbers are coming in, could we go ahead and put up the final poll? Oh, we got the results. So there they are. You can all see them. We don't have a lot of poultry people on the line. I know if we did, we would, the monitoring the eggshell temperature for development would be high on the list as well. So thank you, Dave. One more poll question before we go to question and answer. If you used PLF technologies that require transmission of data from your farm to the cloud, your top 2 main concerns would be, and if you only have one concern, that's fine, but 6 options here. Number 1, no concerns about the cloud. Secondly, privacy violations. Third, poor internet connectivity. Fourth, data propriety rights. Fifth, increased labor demand on my staff. And then 6, other, please share in the chat. Oh, so if you had other ideas that aren't included here that are concerns of yours about the cloud, that your data going up into the cloud, please just type it into the chat line. Or if none of these seem reasonable to you, just type not applicable. And I think Dave and Megan can probably have our results here fairly quickly. But while they're getting it, I want to thank everyone for sending a lot of questions in, including some that came in by iPhone that I have on my phone right now, which I thought was really intriguing. And there's the results right there. So poor internet connectivity was a concern, and I know we all experience that on occasion. So that's a legitimate concern. Let's move on then to our final Q&A session. We had a question that came in, and I'm going to paraphrase it again. And Janice, I'm going to invite you to start with this one, and then maybe Zhao would say a word about it. But if you have animals that are worth less on an individual basis than the PLF technology to monitor or manage them would cost, have you thought about ways that PLF might still be used for you?
So this definitely is something I've thought about a lot, because I do quite a bit of my work with laying hens in aviaries. And, of course, we've got thousands of birds in a single group that all look alike and, are often going to be worth less, especially than any body-worn sensing technology. So one thing I've been trying to work out is how to do like a sampling of the animals to come up with a sentinel kind of population. But thinking about who you choose and where in the barn you may choose to monitor those hens and things like that, you could think about kind of targeting either specific animals, or if you're using a camera-based technology, certain areas of the barn. So ways to kind of maximize the information you're getting without necessarily absolutely covering everything or every animal in the group. So those are some kind of maybe initial ideas for how to overcome that problem.
Thank you, Janice. Zhao, would you like to add anything to that?
Yes, I have something to add that is related with the large adoption of different sensing technology. In the PLF, usually the whole idea comes related to putting a lot of sensors and collecting as much as we can in terms of data. But at the end of the day, I think the beauty of using that is solving more complex problems using less resource in the sensor technology too. So if we can measure fewer animals and get the same result, if we can collect less data, but more important data, and get better results, if we can get less redundant data, right? So a lot of the imagery collected are the same. A lot of the sensor data that we keep collecting, they look the same in the database. So how you optimize data collection, right? This will reflect computational costs, all terms of resource to analyze and to store that information. So I think I'm very aligned with Janice's position in terms we need to optimize the resource and not necessarily put every sensor in every animal. That's something that needs to be taught.
Thank you, Zhao. We are after 12 o'clock. I want to thank everybody for staying on. The panel has agreed to stay on and answer other questions as long as people are interested in chatting about this. We're going to open it up in just a minute and to the audience if people want to comment. We did have another question come in, though, that I thought was really interesting. And I think maybe we'll turn this question around to the audience and give them a chance to answer it. It kind of speaks to Juan's presentation. It came in while he was talking on the iPhone. The question is, do you see other ways precision farming could be used to manage animals, or other uses for the data that could add value or reduce expenses? And Juan, while people are thinking about that, we're going to invite the audience to share what they think would be really useful, things that they think they'd really love to see you guys work on. But Juan, do you want to add anything before we turn to the audience while we give them a chance to think about this?
Yeah, what I want to add on this is reflect one of the answers that Tomás gave today when he talked about business models. So the use of this data will be about someone's business model, because whether it are companies selling new products or feed and medicines, things like that, or equipment, or it's a breeders association, consumers associations, or farmers. There's for sure useful information that can translate into money for them. So it will be up to the stakeholders of the animal industry, the livestock industry, to come up with these uses for the data.
Thank you, Juan. I think Megan has opened it up. If anyone would like to ask a live question now, they're welcome to.
Raise their hand so that I can open the audio if they want to ask a live question.
And Megan, I can't see that, so that if you have any come up, please let us know.
Absolutely, and then feel free to put it in the chat or the Q&A as well if they have additional questions.
All right, and while people are thinking about that for a minute, I want to thank all of you for Zooming in today. It's been a lot of fun for us. Yeah, it's been a good learning experience, I think. I think, again, the panel is willing to stay on and answer any questions that you have. And thanks to Megan and her crew for holding the lines open. While we're doing this, also, if you're willing to take just a minute and answer once we're through with this section, if you're willing to stay on for a minute and answer a post-program survey that we put together, we would be most grateful for that. We are academicians, and I know many of you online are too. We measure everything, and we rely very heavily on your feedback to help make future events like this even better. So please stay on if you're willing. If we don't have any questions, Megan, did we have anybody that wants to ask a question live?
Oh my, actually, yep, 1 second. Somebody just raised their hand. So there we go.
Okay.
I'm to unmute.
Is that Professor Rosa?
Thank you very much. Thank you, everybody, for very interesting talks. I want to go back to the comment by Thomas on terms of the business model and the difference. We may need and we will have different business models, because I see PLF as something that can help. Things overlap, but let's say more animal-centered tools that you are trying, for example, to help with welfare. Of course, quite often you help production just by helping with the welfare. But let's say animal-centered technology helping with the animal welfare, others helping the farm saving time or labor, and others maybe customer centered. So that's, I think, the business model will change a lot depending on where is the benefit of the application, right, Thomas?
Yeah, I completely agree. And that's why I said at the moment, I think the target is efficiency, right? Because farmers can see, okay, if I can't achieve the level of efficiency with me and my staff, well then, if the technology can support, I'll pay for that once I see a return on investment. But yeah, I'd see in the future as a consumer, it becomes more interested in welfare, which is really happening at the moment. We're seeing that particularly in Europe at the moment. Consumers are asking for more high welfare products. Then there is, of course, other business models, for instance, where supermarkets would like to benchmark farms in terms of sustainability criteria, including welfare, and then differentiate their products on the shelves so that they can sell higher value products to the consumer, because yeah, these animals have been in a higher welfare than usual, put it that way, situation. So for sure there's different business models, but I think we have to start off on the business model that makes sense for the farmer. That's
Thank you.
Tammy, did you want to weigh in on that?
Actually, there's a question that I want to answer on the technology being used to help design the barns that came up in the Q&A.
Good, I didn't see that. Please do.
And so Yeah, so as we collect precision animal management data, I think we can really use that data for 3 different applications. First of all, the development of new technology, which is really what we talked about today, which is using it to develop tools to help producers. But the other 2 things that we can do with that data, one of which is looking at the animals in a way, interact with the environment in a way we've never been able to do before. And that really lends itself nicely to engineering design of animal facilities, and enrichments and pen layouts and all of those things that we've never ever been able to get at before. And the third item that we can really look at is looking at developing a way that we can look at individual animal response to different things. And that goes back to the genetics of the animal and being able to develop, we call it novel phenotypes. And then we can work with geneticists to maybe select animals that do better in a certain situation than another situation. So all of this really, really will help us move animal production to a place where we can do better animal well-being and higher production, all in the same sense.
Thank you, Tammy. Janice, would you care to add anything to that?
I think Tammy did a really great job of capturing that. It could also allow us to tweak management protocols too. So yes, we could maybe change the physical structure of the barn in certain ways, but also think about maybe when we time the doing of certain things or how we do it, because that might also cause patterns of behavior and interactions with the physical environment in the pen too. So, do we break feeding up into more times during a day, for example, or do we run the manure belts at certain times of the day based on the other responses that we're seeing with the other features in the environment? So yeah, we can use it to inform both our building design, the materials we're using, the types of feeders or waterers, those kinds of things, types of enrichment, and then also, yeah, how we manage as humans and interact with the animals and the environment in there.
Great, thank you. Madonna's got her hand up. I just saw it.
It's not a virtual hand. I think one of our objectives was to present this virtual PLF day or field day to our educators and farmers and all of those working in the agricultural industry, and really to capture more ideas. And one of the things that comes to mind is that we talk about using PLF to determine estrus detection, but for farms that have reached 90% farrowing rate, it's probably not about estrus detection, but there's 10% lost. And where do producers think that 10% loss is? And that's why we're hoping for that two-way communication. So many of the panelists are engineers, and to have that opportunity to have the communication between veterinarians, farmers, or producers, and then the engineering aspect of it, that I think that'll move things very quickly. Thanks, Dave.
Good point. Thank you, Madonna. Yeah, there are pigs that are not accounted for in the numbers born and weaned versus the numbers that are go to market. And that's a good question. Where do they all go? And obviously they know where some of them go, but there's certainly some potential here for helping with that. Megan, were there any other questions that people wanted to ask live? I want to thank Professor Rosa for asking one, but anyone else want to talk about anything right now?
I think things have slowed down from what I see.
Say that again, Megan.
I think things have slowed down. There's no additional hands raised. I don't see any other open questions.
Okay, then I want to thank everyone one more time. And Megan, how do we do the post-program survey? Do you pop that up right now, or do you do they get that in the mail? I can't remember.
So it will come out when they close their browser. And I've also put it in the chat for everyone, along with additional resources up on our page, along with the event recordings. So those have been posted there so that people can view those afterwards if they so wish. And then the survey will pop up when you close out of your browser.
Thanks, Megan. That's great. And again, please take just a couple of minutes to do that survey. It would really help us out a lot. And your effort will not be wasted. We'll look at those numbers very carefully going forward. And thank you so much. And I want to thank the panelists. They did a great job today, I think. And Megan, I want to thank you and your team for all of your hard work. I think for our first virtual PLF day, I think things went pretty well. So thank you so much, everyone.